So this is objective 3.2D. Today we're going to be solving compound absolute value inequalities. That's your objective. It's not really any more difficult than yesterday's assignment. The problems just take longer to solve, but you don't have to learn anything new to solve them. So let's start off with the vocabulary of what is an absolute value compound inequality, or a compound absolute value inequality. Doesn't matter how you say it, they mean the same thing. So let's define this as some number A is less than the absolute value of some number X is less than the absolute value of some number B. That makes it a compound statement, right? And it's got an absolute value right in the center. Because it is a compound inequality, it's one of those and statements. It has to be true for the first inequality. It has to be true for the second inequality. Therefore, you're looking for an intersection. But in this case, the absolute values, they have to both be solved twice. So we call this a double inequality. Therefore, it will have a double intersection. So you will be looking for two intersections today versus just one. Okay? So remember that. It's a compound inequality. Therefore, we're looking for the intersection. It's going to be a double intersection because it's absolute value. And you have to solve them twice. Okay. Then we have another vocabulary term here, and that's the word constraint. A constraint is a lot like a restriction. It's a limitation on your X value so it's also, another word for it would be a restriction of your domain. However, we're not really going to talk about them as functions right now. But when we come back from Christmas break, we will be talking about constraints on your domain. So we just want to bring that into our vocabulary and what we talk about. Okay? So a constraint is just a restriction. What are we saying X is? What are we saying X is not? Where's the constraint? Where's the number that breaks the answers from the solutions and the non-solutions? Okay, so here we go. We're going to start with the steps for solving a compound absolute value inequality. First, we're going to make sure to reorder from least to greatest if necessary. When we're solving compound inequalities, we like for them to be least to greatest. That way, when we see the constraints, we can graph right between them. It's the proper way to work on them. And then step 2, we're going to separate. They're in the same statement. We're going to separate them. And then we're going to solve each inequality twice because it's an absolute value, so you have to solve it for the positive and the negative to find the constraints. Those are the numbers that separate the answers from the non-answers. And when we find the constraints, each one will provide us with a part of the solution or a partial solution. So each constraint will give us part of the answer, but not the full answer. After we've done all of that, we're going to graph the partial solutions all on the same graph so that we can find the intersections, plural, so that we can identify the full solution, all of the numbers that would satisfy the compound inequality. Then, of course, we'll write the solution in interval notation because that's how we do it. Okay, so that's this process. And here we go with your colors. So make sure you got your colors ready to go, uncapped or whatever you need them to do. First, I'm going to ask you the question, number 1, step 1, is it ordered least to greatest? 0's on this side, 3's on that side, yep, least to greatest. So we don't have to do step 1, we can skip it. Step 2 is to separate the inequalities. So basically what I'm going to ask you to do is we're going to solve that inequality, and then we're going to come back and solve the other inequality. So we're going to separate them into two different problems. Okay, so I'm going to go back now to my blue problem, and listen, important, hear my words, rewrite the blue inequality so that the absolute value is first. So we're going to do a reversal of the first inequality. So the absolute value of x minus 5 is greater than 0. Just reverse the whole thing, flip the whole thing around, and then leave a little space. We'll do the second one. And you don't have to reverse it because the absolute value is already in the proper position. It's first. Okay, so now we've separated them. Now what we're going to do is solve each of them twice. So first thing we do is ask ourselves, is this possible for x, absolute value of some number, to be greater than 0? Yep. So we can solve it. First time we solve it for x minus 5 is greater than 0. Since it's a greater than, we have to write them separately, you know. And the second time we're going to do x minus 5 is less than 0. Yeah, we can't do negative 0. There's no such thing. But we still have to do both versions of that problem. There's not very much that's going to be constrained from this. But let's go ahead and finish it. So we'll add 5. I think I'll just work all the way horizontally here. So we get x is greater than 5, or x is less than 5. So those are some constraints. But that doesn't constrain my answer very much. Basically, it's saying everything but 5 is the answer. But that's only the answer to the blue part. We still have to take into consideration the answer to the red part. So now we're switching to the red. And we ask ourselves first if it's possible. For an absolute value to be less than or equal to 3, is that possible? Absolutely. Since it's a less than, I can write it as a compound inequality, just to save a little time. You don't have to. You can separate and write twice if you want. But I would prefer to just tuck the negative 3 on the left, drop the absolute value, less than or equal to positive 3. When it's a less than statement, I'm allowed to do that. And then I would just add 5 to all 3 sections. And I would get my other constraints. 2 is less than or equal to x is less than or equal to 8. And so now I can see all of my constraints. So in my first set of data, well, first I'm going to look at my constraint numbers. I have 5s and 2 and 8. So I think I'll go ahead and just put them on my graph in their proper spots. Hey, in the back, can you see that, or do I need to make it a little bigger? You can? Okay. All right. So I've got them all numbered out. I'll work with my 5s first. X is either greater than 5, which means it's going to go to positive infinity forever, or x is less than 5 according to the second constraint. So as you can see, in the blue inequality, everything but 5 will make this true. But now we have to take into consideration that only the answers that are true for both of them can be true for the entire inequality. So if x is between them, and we have to use brackets, I believe, because of the equal sign, we're looking at this section of the number line all the way through. And people, we're looking for the double intersections. So you're looking for your double lines. which occur between 2 and 5, and 5 and 8. So if you are going to use the double lines on your graph, and you're going to look for the overlap before you finish the problem and you walk away from your graph, because this graph is not the correct graph. It won't be correct until you somehow identify what the solution is. So I would use something like maybe a highlighter, or I would erase the stuff on the outsides where they don't overlap, something to indicate that the solution should be just between 2 and 5 and 5 and 8. Okay? So a highlighter would probably be helpful if you're going to use the double lines to help you answer the question. Solution in interval notation would be from inclusive 2 to 5 non-inclusive, union with non-inclusive 5 to 8 inclusive. So basically what I'm saying is any number in either interval will give me a true statement when I plug them back in. Now you don't have to do the check, but I'm going to show you that this is true. Let's pick a number outside of our solution set, like for example 0. If I were to plug a 0 in, which part of this statement would be false? The first inequality or the second one? 0 is less than 5, right? That's true. It's less than or equal to. So that's not true for that part. So we certainly didn't need that section of the number line. Let's pick a number inside here like 3. So I'll change it to a 3. That should be true. What's 3 minus 5? Negative 2. Absolute value of negative 2 is 2. 2 is between 0 and 3, so it's good. Then, of course, you could continue to pick points just to prove it to yourself and help your brain make connections. If you want to, you could do checks. Okay, so do you have any questions before we move on? I want to keep this video somewhat short, so let's go to the next one. So first I ask you the question, is it written least to greatest? Okay, so next then I'm going to pick up my colors and I'm going to start separating. And I don't expect your homework to be color-coded, but I think your notes should be. So we're going to solve this inequality, and then we're going to come back. We are going to come back and solve the second inequality. So we'll separate, but remember that we're looking for an intersection because this is a compound inequality, but double intersections because of the absolute value. So the first time we're going to solve, what did I do first on that? What did I do first? I flipped up. So the absolute value of x minus 4 over 3 is greater than or equal to 2. Reversed the whole thing. Switched to my second color, gave myself a little room to work. The absolute value of x minus 4 over 3 is less than 6. Now that they're separated, we have to solve them both twice. Do you agree? Yes? No? Maybe so. Okay, so we get x minus 4 over 3 greater than or equal to 2, or x minus 4 over 3 less than or equal to negative 2. And we'll go ahead and solve that one first. So I would suggest we clear the fraction out of there so that we can solve for x. So I'm just writing in pencil here so that I can indicate that this is not the original thing that I did. I'm clearing the fractions, so I'm going to multiply each section times 3 so that I can clear out the denominator. Then I'll go back to my blue pencil. So I get x minus 4 is greater than or equal to 6, or x minus 4 is less than or equal to negative 6. And then continuing on, I'm going to add 4 all the way across to all 4 sections here. And I get x is greater than or equal to 10, or x is less than or equal to negative 2. on the second time, I'm going to ask you if this is possible. Can I have an absolute value be less than 6? Yeah. And since it's a less than, I can write it as a compound, right? So negative 6 less than x minus 4 over 3 less than positive 6. Okay. Then, again, we would clear the fraction. So I'm going to go ahead and do that with my pencil just to indicate that that wasn't the first step of that process. I think I'll also separate here. All right, so I get negative 18 is less than x minus 4 is less than positive 18. And then I'll add 4 to all 3 sections to isolate the x in the center. That gives negative 14 is less than x is less than 22. Okay, so now I'm going to go graph my solutions, or my partial solutions, using my constraints. So I'm going to look at all of my constraints. I had a negative 14 and a 22, and a negative 2 and a 10. Well, I think these are my least and greatest, are the negative 14 and the 22. So I'll put those on the far outsides. And then I'll switch and put my negative 2 and negative 10 on the insides. And I'll go ahead and graph my blue, since I have my blue ones up. X is greater than or equal to 10 would go this direction. And x is less than or equal to 2 would go to the left forever. And then I would switch to, so those are constrained but not very much. So that's only true for the first part. Let's go get the rest of the truth over here in the red part. X is between 14 and 22, non-inclusive. So that would be this section here. Then what you're looking for is the obvious overlap, which would be here between negative 14 and negative 2, and between 10 and 22. Now, I told you at the beginning that I would give you another option for this, and so I'm going to do that right now. And then I'm going to challenge you to do the last problem on your own. So, as I was working these problems out today, one of my students, Yoselin, in second period, she was doing the bell work. And she did a really interesting thing in the bell work. And I thought that I would share it so that you could use it as an alternative if it makes more sense to you, or if you feel it's a little bit more efficient. Just have to be careful with the signs. So just check this out. Here is what she did. She took this statement and she dropped the absolute value and left it just as it was. And then she reversed it. She put the negative 6 here. Same symbol. She changed the outsides to negatives, made sure she put them least to greatest, so they flipped sides. And she also remembered to take the sign with the 6, so it was a less than. She took the sign with the 2, and it was a less than or equal to. It was a greater than or equal to, but they still look exactly the same. The only thing that switched were the outsides. They both became negatives, and they switched places, okay? And the inequality went with the number it belonged to. So the 6 had a greater than or less than, and the 2 had a less than or equal to, greater than or equal to. So when you solve this one, check out what happens. It's pretty interesting. Clear the 3, right? So we get 6 is less than or equal to x minus 4 is less than 18. You with me? Yes? No? So that's 10 is less than or equal to x is less than 22. Do you have that in your graph? From negative 10 to 22? Guess what I'm going to get when I solve the negative version? Negative 14 to negative 2. Watch what happens. I'll multiply times 3. Come on. Times 3 times 3. So negative 18 is less than x minus 4 is less than or equal to negative 6. Add 4, add 4, add 4. So that is negative 14 less than x less than or equal to negative 2. I think that's kind of interesting. I don't know. Do you? I think it kind of is. Because then you don't even have to worry about intersections. You're graphing from negative 14 to negative 2. That's that one. And then you're coming back and graphing from 10 to 22. That's that one. Solution. Done. It was really interesting. And we tried it with a couple and it continued to work. So we did a little experiment and it worked every time. So if you would like to adjust your process to that, I'm offering that as an alternative. Just be really careful to move the inequality with the number. Do you know what I mean? The 2 and the negative 2 get the equal to sign. The 6 and the negative 6, no equal sign. Okay, so be really careful about that. All right, last problem. You're going to do it. I'm just going to start you on it. And I'll give you the answer to make sure that, you can be sure that you got it right. So I'm going to ask you this question. Is it written least to greatest? No. So here's why I'm starting you with it. We need to reorder it least to greatest so that it's 4 is less than or equal to the absolute value of 2x minus 1 over 3 is less than or equal to 8. And now it is all on you to solve it. The solution should be from, where'd I put my notes? Here we go. Inclusive negative 23 halves. And you should write this somewhere because I'm going to turn my computer off in a sec. Union 13 halves to 25 halves. I think I'll bring this down a little bit and make it bigger, just in case somebody needs to see it. There we go. Okay, so that is what you should do. That is what you should get. I would like to see that all worked out and completed before you begin your homework. You still have 10 minutes left of class. You can finish your notes, write your summary, whatever. Homework is to do problems 61 through 69 odd, and 62 through 70 even are the extra credit.